I'm particularly passionate about my research because it involves phenomena that affect people directly. During the last 30 to 40 years, we've seen shifts in the numbers, for example, of extreme weather events such as typhoons and hurricanes. We seem to have a much larger preponderance of those systems than previously. The air temperatures have certainly warmed. We have been experiencing more and more intense El Ninos, for example, during the last 30 years as opposed to the last 60 years. So from that perspective, I think the general public can perceive, just from that limited database over a lifetime, that some hints at climate change are occurring. Well, what I would like to instill in the audience is an overall appreciation of how, first of all, how our weather and climate systems actually work. And I will also discuss how some of the global warming aspects are in fact impacting not only our climate system, but also our weather systems as well. In fact, with the addition of more water vapor to the atmosphere, that adds to potentially extreme impacts of heavy snowfalls and so forth. Extremes affect us all in different parts of the world, and every single extreme event that I'm looking at, including short-term weather events and longer-term fast climate events that might be related to a month or two period of storminess, are fascinating from my point of view intellectually, but I also realize that doing a better job of understanding these phenomena will help us both understand and also better forecast the systems so that we can become more aware and better prepared for the extremes.
So good evening, ladies and gentlemen, and welcome to the 2016 version of Mini Science Series at McGill University. It's entitled, as you can see, Weather and Climate Going to Extremes. The series consists of 7 presentations over the next 8 weeks or so, and they essentially carry the message that many global change scientists at McGill have in terms of the way in which our environment is changing, but also the way in which we've created some of these changes and the way in which we're being impacted by them. So please welcome John Gyakum.
Well, the topic here tonight is that of weather and climate. We are going to talk about extremes, but we're going to talk a little bit first about how weather and climate actually work. So to start, I'd like to point out just a couple of pictures to you. The leftmost image is that of kind of a familiar scene that we see in our area. It's that of an ice storm, and interestingly enough, this particular photograph is not taken in the province of Quebec, but rather in the state of Kansas, so back in 2007. So this goes to show you that ice storms are not in any way confined to, as it were, the Great White North, but rather a lot of other places around the world, and particularly in North America. The rightmost picture is something to do with climate. And what we're seeing here in this particular image is a global map of temperatures, average temperatures during the month of February. Here we are in February. And basically the color coding here is rather crudely designed to indicate cold and relatively warm temperatures. And you can see during the month of February, in fact, we have a lot of blue in the northern hemisphere because this is our winter. In the southern hemisphere, it's their summer. So anyway, this is a map of climate, if you will, based upon a temperature field. I've got a couple of definitions here. There's a lot of words here. The definitions of weather and climate in particular, as indicated by the glossary of the American Meteorological Society. So weather basically involves processes that are related to day-to-day metrics such as rain, snow, wind, temperature extremes, and so forth. And normally we think of weather in terms of timescales of only 1 or 2 days, or perhaps in the case of some severe weather, thunderstorms, tornadoes, maybe just a few minutes in fact. Climate involves a lot of other factors. Normally we think of climate as being a state of the atmosphere that represents some type of an averaging of a quantity like temperature or dew point temperature or an average amount of precipitation. As you will see way down here in the definition, our definition of climate has actually broadened and evolved in recent decades in response to the increased understanding of the underlying processes that determine climate and its variability. And I'll try to get to that a little bit later on in this discussion. So we have a quote, and this is an interesting quote. I don't know how many of you have heard this before, but it's climate is what you expect, weather is what you get. And whether this was ascribed to Mark Twain is commonly thought of, not clear, but it is an interesting concept. And what we're looking at here is a bunch of figures, and I've taken these out of the U.S. Climate Prediction Center website for both Ottawa and Vancouver in Canada. And in particular, what we see here is this essentially sinusoidal distribution, the up and down of temperature as we go from month to month during the course of a season. So for example, in Ottawa, we have a fluctuation of temperatures that go from approximately -10 to about 20 to 22 degrees Celsius during the course of a year. In Vancouver, the scale here on the left is a little bit different. It's much more moderate in the sense that wintertime average temperatures there are about 5 degrees C, and in the summer they're considerably more moderate, on the order of 17 degrees C. Now, what is particularly interesting about this diagram is the fact that you'll notice that there are, in fact, fluctuations in the actual temperature. And these figures actually represent the temperature traces that have occurred during the past 12 months. And what is particularly intriguing about this is the fact that when we look at these features, we see that in this bottom left diagram, we see for Ottawa in particular, last winter, during the course of last winter, in particular February, we had a number of temperature fluctuations that were really particularly persistent in their cold anomalies with respect to the climate. And then this past winter, in particular during the month of December, it was very warm. So I think we can say that the fluctuations in temperature that have occurred over the past year are actually anything but what we would consider to be the normal climate state as represented by this nice smooth curve that you see in the picture. And also, interestingly enough, Vancouver has had essentially warmer than average temperatures over the last 12 months or so. Now, if I can go to this line here, the green line on this diagram that represents the average anomaly, the average difference of temperature between that of climate and what was actually occurring, we see that in the case of Vancouver, it's quite a bit above average, on the order of 1 and a fraction degree above average. So this past year has been different from climate. Now the question is this any different from what we would expect from other years? And the answer is no, not really. These nice curves that you see in the climate represent statistics, average statistics, based upon what we have from the last 30 years or so. And that's typically the range of time for a climate record. So finally, when we get to this slide that we really want to see, freezing rain is on the left. And again, this is a picture from Kansas during December 10th to 11th of 2007. The rightmost picture is perhaps one that you've all seen, and that represents the freezing rain event of 1998. And what's particularly pertinent about this is the fact that the range of time that's involved in the leftmost picture was maybe a day or so. What we were talking about in January of 1988 was essentially a 5-day period. And this is very interesting because the length of time involved here in our event of 1998, and I'm sure a lot of you have had experiences during that 1990 event, really not only lasted for nearly a week, but the impacts themselves lasted for much longer than that. And it's interesting to note that this particular event had ramifications and implications for the next several weeks and, in fact, months of the year. So, for example, in my hometown of Côte Saint-Luc, we lost power for about 3 days. NDG lost power for an average of 10 days or so. Off-island, the power outages lasted for about a month and even beyond that. So our entire winter was really defined by that one ice storm. it's interesting to note that if one looked at the climate records for this region of the world for the month of January of 1998, we would see a warm anomaly. And so if one were to just look at the climate map of temperature anomalies with respect to the 30-year climate, we would say, aha, it was a mild winter. So you see, that doesn't tell the whole story, not even close. Okay, so I'm going to give you some examples of extreme weather. And this is an image that a lot of us may think of in terms of our own memories. The New Orleans case of 2005. Most of New Orleans is actually located below sea level. Hurricane Katrina clobbered the area in 2005. It could have been much worse. It happened to be a Category 3 hurricane. You can see the evidence for this offshore, a very significant eye-like circulation around the area in the Gulf of Mexico. And the interesting thing is the storm itself died or was dissipating by the time it reached the coastline. So interestingly enough, you might think, well, this doesn't have a whole lot to do with us, does it? But if we consider what happened several days later as this hurricane migrated farther to the north, turns out that the remnants of Katrina actually produced about a month's worth of rainfall in the province of Quebec in our area just a few days later. So this is a big problem, particularly with respect to climate change, as more and more tropical disturbances begin to migrate farther to the north. It has a big impact on us, not only in terms of the wind, but also in the context of having a lot of rain. So this is another example of an extreme weather state, a tornado. Just so happens that our McGill chase team that was led by Dr. Iyad Atola went on a tornado chase in May of 2013, and they really hit pay dirt by being able to view this terrific-looking tornado over Bennington, Kansas. Interestingly enough, I mentioned Kansas before because we saw ice storms, and lo and behold, Kansas has had this tornado too. So that's an area of the continent that's clearly associated with a lot of extremes. The chase team managed to be very fortunate in the sense that they were able to just stop their cars and view this tornado because it actually was quasi-stationary during the course of time. Another example of extreme weather relates to floods. And in particular, the rightmost picture is another case that probably resonates very well with the audience because in Calgary, during the year of 2013, there were extraordinary floods that lasted for several days. Heavy rains in the foothills of the Rocky Mountains, producing incredible amounts of flooding. So the one on the left is fascinating in the sense that what we're looking at here is the Mississippi River flood case of 1993. And what was intriguing about this case was that, yeah, it was a weather event, but it was really also a climate event as well. And what is particularly intriguing about this case, if I can go back here, if you look at the tributaries that flow into the Mississippi River and the Mississippi River itself, we will be able to see that the range of coverage of water is fairly well contained. This is a picture taken, I think, about a year or so prior to the Mississippi River flood. And the leftmost, the bottom panel shows an illustration of what was happening during the Mississippi River flood, in which there was a massive amount of flooding not only over the river itself, but over the attendant tributaries as well. There's a levee system along the Mississippi River, but many of these levees were compromised. And many of these areas in the floodplain, excellent agricultural areas, were inundated with water. So heavy snow, and this is another topic that we as Montrealers think a lot about, and okay, properly so. It's been snowing out this afternoon, and that's what you'd kind of expect to see during the month of February here. We've had a lot of other weather elements here as well. But I'd like to point out that the pictures that I'm showing you here actually represent photographs from Washington, D.C. This happened to be a case in 1922. It's called the Knickerbocker Storm. because what happened was that the Knickerbocker Theater that you see here was actually collapsed during the course of this storm. There were a lot of people, just like we're sitting here, enjoying themselves, maybe enjoying themselves more than you're enjoying this talk, but enjoying a show. And all of a sudden, the roof collapsed, and there were many, many fatalities, nearly 100 during the course of this storm. What I would like to point out is that this particular snowstorm produced 70 centimeters of snow. And if we compare, for example, the record 24-hour snowfall that occurs in our area, that number happens to be about 40, 41, or 42 centimeters. So interestingly enough, despite the fact that we think of ourselves as kind of the snowfall capital of the world, our 24-hour records do not come close to what happens in other areas of the world. Washington, D.C., for example, had another snowstorm this year that amounted to upwards of 50 to 60 centimeters. But interestingly enough, it's interesting to note that Ottawa, just a few weeks ago, broke their snowfall record, broke their 24-hour snowfall record with an amount of 50 centimeters that busted its previous record of about 40 centimeters. So that was an intriguing case, and perhaps, just perhaps, this is a representation of heavy snowfall records migrating northward during the course of years, possibly associated with the air masses that are typically associated with the Gulf Stream, for example. And that's one of the reasons why Washington, D.C. has such heavy snowfall records, because they are so close to the Gulf Stream and so close to subtropical air masses. So I'm going to go into a few examples of extreme climate locations. And in particular, we will go to the country of Chile, which you see off to the right here, and you'll see a coastline. And it's interesting to note that, well, yeah, this town of Arica, Chile is located on the coast. And if you look at the number here, they average just a fraction of a millimeter of rainfall every year. Almost, they've gone several years without any rainfall whatsoever. So the question is, why does this even occur? Well, and the reason it does occur is that despite the fact it's located on a coastline, the Andes Mountains are in fact located directly along the coast of Chile, and they're blocking the predominantly easterly flow in that area, and the airflow is forced to go down and subside and produce dry weather. Accompanying that is the fact that there's the Peruvian ocean current, which happens to be very cold and produces relatively cold conditions and subsiding air. So this is an area of the world that is particularly dry. Well, here's another area that's the opposite. An area of India, which is in the foothills of the Himalaya Mountains. And this particular location, which is not all that far from Cherrapunji, India, a place that we studied a lot when I was a graduate student, Mawsynram, India, gets upwards of 11 or nearly 12 meters of rain every year. So its elevation, it's situated in a vicinity that is affected significantly by the monsoon circulation. But we can know also that the elevation here is about 1,400 meters. And so if we look here at some of the people who are working in this area, if you look at the bottommost image, we see folks walking around with something over their heads. And these are actually what we would think of as umbrellas, but they're really fancy umbrellas because they allow people, in fact, to function and work in this environment. So these items are actually called nups, and they're made of bamboo and banana leaf. And I would like to have one. I think it's great, because walking around here in the rain is really kind of rugged, particularly with the wind. So these people really know how to live. Another place in the northern part of Honshu Island in Japan, Sukayu Onsen, Japan. They average about 58 feet or 18 meters of snow every year. Their elevation is about 900 meters. They're influenced heavily by the significant amount of snow that comes from air flowing from the Sea of Japan, cold air masses that are modified by the Sea of Japan in the prevailing westerlies from the Sea of Japan, and there's a significant amount of snow. And you can see the bus here, the tour bus that's going along a road. They never close the roads. They keep them open. So that's all very exciting. Now, I'd like to talk about another extreme climate event that happens to be pertinent because we are in a position of having or being in an El Nino right now, even as we speak. This topmost picture is an example of a time series of an index of the El Nino phenomenon. And the El Nino phenomenon really relates to the relative warmth in the ocean that exists to the west of South America. So just to give you a picture of what's happened during the last 60 years ago, I'm going to point out three major events. The first event is 82-83. The second event is 1997-98, and it just so happens that that was the year of our ice storm as well. So during the course of an El Nino, a lot of times weather forecasters will point to significant warm temperature anomalies or unusually warm winter weather in this part of the world, and that is associated with air masses coming from the subtropics and producing rainfall, not unlike we had last evening. We had quite a bit of freezing rain last evening. So to give you a picture of the overall local circulation that we see here in this vicinity, these trade winds that are typically blowing from east to west over the Pacific are modified to the extent that they're sometimes reversed. And in the vicinity of where South America is, right in this location, we have air that oftentimes tends to go up, and in particular the air is going up quite prominently over the central part of the Pacific. So there's an unusual amount of warmth and attendant rainfall over the central part of the Pacific. While at the same time, as we go to the west, there's a lot of subsiding motions with its attendant relatively cool and drier air. So this is associated with the ocean waters that are normally quite cold along the west coast of South America. The attendant cold downwelling waters in this vicinity, the attendant cold waters, are actually associated with heavy-duty nutrients that allow for the fishing industry to exist very well in Ecuador. And during the time of an El Nino, during a warm event, that is suppressed to the extent that the fishing industry is pretty much shut down. So that's some of the local effects. As I pointed out, in the western part of the South Pacific Basin, oftentimes with the subsiding motions, areas of the world like northern Australia and Indonesia have very dry conditions. And what is happening here is an example of, from a satellite image, of a massive fire that was occurring in the vicinity of Indonesia. And during the course of this event, this was during the 97-98 El Nino, this was releasing as much as 2.5 gigatons of carbon dioxide. So a significant fraction of release of CO2 compared with what human activities are doing in that vicinity was also associated with this wildfire. Again, with respect to an El Nino, we have oftentimes massive amounts of rainfall that occur along coastal areas of California. And areas of the coast, not only do they get rain, but because of the rather unstable landscape, we have mudslides and houses that are destroyed. It's interesting to note that during the course of this particular El Nino this year, even though we have a strong El Nino, Southern California has remained relatively dry. So some of the tweaks, some of the perturbations that exist with respect to weather that is associated with El Nino can be changed based upon exactly what El Nino is doing in certain areas of the world. It's been warm here, it's been warm in the west, but it's also been relatively wet in the areas of Seattle and Vancouver, and that's not particularly usual for an actual El Nino. So there certainly are tweaks to the climate system based upon some of the internal variability of the atmosphere during the course of even an extreme El Nino of what we're seeing now. Okay, so what I'd like to do now is say just a few words of another extreme climate event, and this occurred last year, February of 2015. You'll note it that at the very beginning of this discussion, we mentioned the cold anomaly that was associated with Ottawa, and that really was pervasive over much of eastern North America. So if I can show you here with the arrow as best I can without tweaking the system, during February of 2015, Montreal had record cold temperatures. What was particularly pertinent about February was that we had not one day, not 1 second in which the temperature rose above 0 degrees Celsius. And yet, at the same time, we actually did not break any individual daily temperature records. So that's an interesting fact. Despite the fact that we were the coldest on record, if you look at this entire map, it's pretty much red except for this rather isolated region of eastern North America. So globally, this was actually the second warmest on record, with records being taken since 1880. So the question is, a logical question here is this a manifestation of climate change? We have the atmosphere, which seems capable of really producing very interesting patterns, even though the globe is warming. So for example, last year, right along the east coast of North America, we saw a tremendous number of snowstorms that occurred. And those snowstorms that occur along the east coast of North America, in concert with the very warm Gulf Stream current of the North Atlantic Basin, produced tremendous amounts of either rain or snow. Washington, D.C. got a lot of snow. Boston in particular got a lot of snow last year. We, during our season, had snow. We had no freezing rain to speak of last February. There was no way we could get it, but it was all snow. It wasn't a great amount of snow. Now, if we go a little bit farther to the west in this picture, I'll get to the next one later, we see very, very dry conditions, very warm conditions out west. But in concert with this, there was this tremendous drought that occurred in California. So the structure of these temperature features has a lot to do with the storm tracks or the weather systems. And what was happening last year, particularly in BC, Washington State, Oregon State, and California, was a tremendous drought that was essentially driven by this big ridge of very warm air that was essentially located over the western part of North America. So anyway, it's interesting to note that with this particular pattern of temperatures, the cold area was encompassing Ottawa and Washington, D.C., where all the politicians are located. And so it's interesting to note that if you have a congressman, for example, that doesn't have a passport and never leaves Washington, D.C., and they get all this snow, they're apt to come into a building like this and say, hey, here's a snowball. Are you telling me that the globe is warming? Well, all you got to do is look around the globe and see what's really going on. Now, this is an example of the drought monitoring system that is produced by NOAA in the United States. And what is particularly pertinent about this is this incredibly large region of droughts that existed in California, this rather reddened and dark region in the west. And that particular drought is still going on even this year in the southern part of California, despite the fact that there is an El Nino occurring. So I'm going to say a few words about how the climate works. So this is a picture we show to students in our classes, and I think it's pertinent to show a few illustrations of the overall wind flows here. And I think what is particularly important is the fact that basically the sun is at its strongest on a yearly basis, on an annual basis, right over the equator, and it's very weak in terms of its solar insolation over higher latitudes. And so what this tends to do is that it generates an area of rising motion over the equatorial regions. So this wind flow actually rises and passes up to areas to the north. And what we see here is kind of a basic pattern of wind that flows in certain directions. In particular, at the lower latitudes that flank the equator, the winds are basically coming in from the east. In the northern hemisphere, there's northeasterly trade winds. In the southern hemisphere, we basically see the southeasterly trades. In the north, particularly in the middle latitudes or the extratropical latitudes, we tend to have basic westerly winds, the prevailing westerly winds. And that's one of the reasons why, for example, with the prevailing westerlies over Europe, the winds that do blow from the west tend to moderate the climate quite considerably. So evidence the fact that Labrador is located at approximately the same latitude as Western Europe, and the climate is completely different. That's because the westerlies over Labrador transport a lot of cold air from the continent, whereas the westerlies over Europe, particularly the United Kingdom, transport a lot of warmth into the areas. So what is particularly interesting about this is the fact that with this excess of radiation that is found over the lower latitudes as compared with the higher latitudes, we see this figure illustrating the point. And if this were allowed to go on, we would see a continuance of cooling at higher latitudes and a continuance of warming at lower latitudes. We observe that this is not really happening, so what's really happening is that there has to be some type of a mechanism for heat to be transported away from the excess area of heat in the lower latitudes into the higher latitudes. And similarly, the cold air that we see at higher latitudes is ultimately transported equatorward. And in a similar manner, if we go to the leftmost picture here, turns out that the atmosphere tends to be rather transparent to solar radiation. And what that means is that the sun, as it heats, it basically heats the ground and the ocean areas. And that heat is re-radiated to the overlying atmosphere. And that excess of heat that builds up at lower levels somehow has to be ultimately transported back to much higher elevations. This is an example of how weather is a manifestation, a necessary manifestation of the climate system. So what we're looking at here is a massive cumulonimbus cloud, a massive thunderstorm that's basically topping out at the top of the troposphere, normally about 15 kilometers or so above the surface. And what happens during the course of a thunderstorm is that this excess heat is basically transported turbulently, often massively turbulently, upwards. And that upward turbulent motion is associated with thunder, lightning, heavy rains, and so forth. But it does function. It functions as a necessary component of the climate system so that heat that is otherwise excessively built up near the surface is transported upwards. So in a similar manner, this is an image from the 23 January snowstorm that clobbered both New York and Washington, D.C. The circulation around this low along the coastal regions of the East Coast indicates this counterclockwise circulation with a cold air migrating equatorward over the vicinity of eastern North America and the attendant warm air that's migrating northward to the east. And that's representative of a cyclone. And on a much larger scale, therefore, cyclones are acting to modulate the climate system by redistributing the heat. And that's a necessary part of the climate system. Another example of how weather and climate actually work together is the recent El Nino. And it's interesting to note that last year's hurricane season of 2015 was actually quite benign, quite quiescent. We had a below average number of hurricanes that occurred in the North Atlantic Basin. And this is actually a seasonal forecast that was done very, very well last year because the forecasters kind of got it right. They anticipated an El Nino. And what happens during the course of a season in the North Atlantic is that there is a tendency for the winds to be increasing strongly upwards. And we call this vertical wind shear. So if we take kind of a cloud that is like this, and if I have very strong winds aloft and I shear it off, I basically destroy the essence of the cloud and the coalescence of the heating that goes on with a hurricane. So that's what basically happened during the course of this particular year. Many of the hurricanes that began over the eastern part of the North Atlantic, they tend to migrate westward, but they were oftentimes sheared off ultimately and got destroyed. There are a few individual cases of hurricanes that were strong, but such as Joaquin that hit the Bahamas. But other than that, it was a very quiet season. Another aspect to this particularly quiescent season over the North Atlantic was the strong sinking motion and along with a lot of dry air. So interestingly enough, despite the fact that there was an El Nino that really forced a lot of hurricanes to die off during the course of that one year, the season in the eastern North Pacific was actually quite strong. A record number of hurricanes were occurring there. As it turns out, El Nino has a teleconnection effect to the west of Mexico that allows for not only very limited wind shear, but also very, very warm ocean waters, and that facilitated some very strong systems. So as far as what we actually mean now by climate change itself is manifested in the form of extremes. In this case, an extremely dry climate, a heat wave with attendant dry conditions, flooding, extraordinary amounts of flooding. I will give you an example here of the European heat wave of 2003, and I'm sure a lot of you have heard about this. This particular image gives us some sense of what was happening during this period, in which the land surface temperatures differences from the anomalies were well over a degree or well over 10 degrees Celsius above average during the course of the summer of 2003. It had huge impacts, large amounts of fatalities, particularly in France. The agricultural industry was impacted substantially. Many of the deaths that occurred in France were associated with rather elderly people who basically were not able to travel and were pretty much stuck in non-air-conditioned conditions in Paris in particular. And during the course of this heat wave, a lot of their children were actually vacationing because August happens to be vacation month. July and August are vacations in Europe. Now, this is a representation of the climate for this area of Europe. And what I'd like to point out here, along this one line, we have temperatures that go from left to right, colder to warmer. And in particular, we have a situation in which the mean temperature, the average temperature for this particular area is about 17 degrees Celsius. Now, every one of these little lines here represents what was actually happening over Europe in particular years. And you'll see the labelings here, 1909, 1947, and 2003. 2003 was way, way above average. So the question is, how much above average? And so what I'm doing here is pointing to recurrence intervals of 10 years, and then we have 100 years, and we go to 1,000 years, and yet, lo and behold, look at where we are in 2003, well beyond this. Now, there's a potential problem with a figure like this. There's no question that the heat wave in 2003 was very extreme. One of the issues that we have with respect to understanding the climate system is getting a decent record. I think one of the pertinent aspects of our knowledge of climate is essentially how short our memories are. A lot of times we think of our climate only in the context of what's happening during the last 2 or 3 years. And even those of us who seem like we think we're savvy enough to know about climate, we only go back 30 years. Folks in the audience who really have a lot of age on them may go back 60, 70 years and remember a lot of events that occurred. But yet, that still is not good enough. So for example, just to go back to the ice storm in 1998, when had we ever had 6 inches of ice? Don't know. There was a big ice storm in the early 1960s. We might have had 1.5 inches. But prior to that, this busted all records. So when I'm showing you a picture like this, this is an extreme event, but we really don't know. It's not fair for us to really designate a recurrence interval of as much as 100 years or 1,000 years, because our records really only go back, in most cases, not much more than 100 years. These are approximate surface temperatures or skin temperatures for the flanking planets, Venus and Mars. You'll see, respectively, how warm and cold they are. So it's actually a little bit more complicated than just our location with respect to the sun. So first of all, the primary greenhouse gases that we see in the Earth system are essentially water vapor and carbon dioxide. Water vapor, we'll talk a little bit more about that later on, actually is one of the most important greenhouse gases that we have in our system. But were it not really for the presence of water vapor and CO2, we would actually have a temperature, if there were none of these greenhouse gases, of minus 18 degrees Celsius. Okay, that's globally averaged over all the seasons. I know that we experience minus 18 here once in a while, but I'm talking about a global average temperature. So if we actually have the greenhouse gases, and we do, we go to a number of 15. And that makes ourselves habitable here. We live in a completely different environment had we not had these greenhouse gases to help us out. So what is the greenhouse effect? The sun heats the surface of the Earth. What happens is that the radiation, the sun's radiation, is re-radiated in longer waves out to the overlying atmosphere, and that's responsible for heating up the atmosphere. But you see, as that long-wave radiation is re-emitted into the atmosphere, it is also absorbed and re-emitted by greenhouse gases that include carbon dioxide and particularly water vapor. And that's responsible for what's really warming us up in the atmosphere. The greenhouse gases that exist, and again, what's interesting about this is that H2O is really the most important of the greenhouse gases. But what's interesting about it is that we don't really have a lot of control over how much water vapor we have in the atmosphere. The numbers here range from like 0.1 parts per million at the South Pole to much bigger values, 40,000 in the tropics. And there's a big amount of variability, even in one location like here in Montreal. We range several hundred times over a several-day period during the course of a winter here, and that has an impact on our weather systems as well. So if I go down here to CO2, approximately 400 parts per million, and then we go to the other gases that include methane, nitrous oxide, ozone, Freon 11, Freon 12. Those are also greenhouse gases that in fact are associated with human activities that have an impact on our climate. So why do I bother to mention, for example, methane, which really is an order of magnitude less than that of carbon dioxide? That's because it's a much more efficient greenhouse gas, and it does have a significant impact on our climate. Interesting thing about CO2 is it happens to be very well mixed globally. So you'll see these little fluctuations in the CO2 up and down, and if you really have a sharp eye, you'll notice that this is the seasonal cycle. And what happens during the course of the summer months, and I mean the northern hemisphere summer months, those numbers go down because the vegetation takes up a lot of the CO2. And why is it, for example, that globally we have less CO2 during the northern hemisphere summer? That's because the northern hemisphere is dominated by land and the attendant vegetation. So anyway, the numbers are going up substantially. Climate change. Is this really any kind of a moral issue? So some of the key concepts that we need to consider. Will the benefits from an expanding economy cause suffering from the associated greenhouse gases? Do we try to help our children, or do we let them fend for themselves? How do we factor in the odds of climate change in actually producing a catastrophic event? I'd like to point out a couple of global maps here, which I think are really important. The top one here is a global map of carbon dioxide emissions with the reddened areas indicating the most emissions. And what you can see is that the developed world, including much of North America, Europe, and Asia, and Australia as well, has very high CO2 emissions. However, if we go to the bottom chart and we look at this area of vulnerability to climate change, the risks, as evidenced by the blued areas, are in fact areas that are completely disparate from those areas that are producing the CO2. So as an example, what we're looking at here are areas, for example, of Asia and massive amounts of populations who have migrated to urban areas that happen to be located near sea level. And with that, with the attendant rise in sea level and with the attendant increase in the number of storms, these people are very, very vulnerable to climate change-related catastrophes. So the bottom line is that in terms of the climate of hurricanes and typhoons, we seem to be getting more cataclysmic events in association with climate change. And at least anecdotally, we might have seen this over the past couple of years with respect to, for example, the cyclone Winston that clobbered Fiji in very recent days. Typhoon Haiyan that's clobbered the Philippines. These are super typhoons with record-breaking amounts of wind and intensity. So just to give you an example of what happens with respect to global warming, we've seen that the globe's temperatures are rising. With that, there tends to be more evaporation that occurs from the oceans. With that, there's more water vapor in the atmosphere, and there's a higher moisture content. I mentioned that the water vapor itself is in itself a greenhouse gas. So what we're doing here is producing a feedback. Not only are we getting more warming in association with the CO2 emissions, but in concert with that warming, we are increasing the amount of water vapor in the atmosphere, which is in itself a greenhouse gas. A recent study at NASA has suggested that the feedback here, this positive feedback on the warming, actually doubles the amount of warming that would be associated with no increase of water vapor at all. So it's this type of feedback that is quite concerning, and we don't have any control per se over the amount of water vapor that exists in the atmosphere, but it does seem to be increasing with time. Dr. Gerald Meal, who's a climate scientist, a renowned climate scientist at the National Center for Atmospheric Research, will address the question of what do steroids in baseball have to do with climate change. So let's hit it and see what we can do with this.
What do steroids in baseball have in common with climate change?
Well, imagine a baseball player who's been taking steroids. This baseball player steps to the plate and hits a home run. And you ask the question, was that home run due to the steroids? If you look at the number of home runs he hits over a season when he's taking steroids, and compare that to a previous season when he wasn't taking steroids, it is only then that you can figure out that the steroids have made him more able to hit a home run because it's made him stronger, and the chances of him hitting a home run are greater. So by adding just a little bit more to those naturally occurring steroids in the human body, we change the background base state of our systems.
Okay, got it. But a lot of bad things happen when you take steroids, right?
The greenhouse gases that we're adding to the atmosphere from the burning of fossil fuels are the steroids of the climate system. The atmosphere has very small amounts of greenhouse gases that occur naturally. So by adding just a little bit more of those greenhouse gases by the burning of fossil fuels to the air, we change the background state of the climate system. We increase the temperatures just a little bit, but that increase of temperatures is enough to shift the odds toward a much greater chance for extreme heat events and extreme precipitation events.
Normally, you'd expect record lows and record highs to balance out over time. But now we're getting almost 3 record highs for every record low.
So just as a baseball player on steroids can occasionally strike out,
You're out! No!
climate system with increased greenhouse gases can still experience record cold temperatures. But the chances of record high temperatures are still much greater.
And that's what steroids in baseball have to do with climate change. To find out more about climate change and extreme weather, check out ucar.edu/atmosnews.
Again, just to point out, last February, it's interesting to note that we had a record cold month, but I should point out that a lot of people's perception of the climate here, we have snow, but honestly, when I talk to people about the climate of Montreal, a lot of times I hear the words, oh, minus 30 degrees Celsius. Well, guess what? The last time we had minus 30 degrees here was in January of 1994. Okay, so it's been 22 years, almost as long as when the last time the Canadians won the Stanley Cup. So this is a good reference for climate change. It's the IPCC report, the fifth assessment, and I urge you to go to this website. There are a lot of research questions that are still outstanding, and I'm just limiting my thoughts to a few here. How climate change itself changes the weather, and I think this is particularly pertinent because we want to know on a day-to-day basis what the weather is going to be, right? Quite honestly, I don't think if the temperature changes were uniformly 2 degrees or 3 degrees higher than average, we would care very much. But those relatively small incremental changes can have huge consequences for the frequencies of extreme weather conditions. A good example was, in fact, the Ottawa snowstorm a few days ago. Other examples include the super typhoons. Modulating the system by incrementally increasing the amount of water vapor and changing the air masses ever so slightly produces a much higher likelihood of extreme weather conditions. So among the questions that I'm asking here, and this is an area of active research, many of these are, where will the climate change related extreme weather systems be located? A legitimate question is, I showed you this map for February of 2015. Why the heck was the cold air over us? Why wasn't it somewhere else? And to be honest with you, I'm not entirely sure. I had a student who did some work on a PhD looking at Arctic sea ice, and you'll hear about that in a couple of weeks, looking at how Arctic sea ice loss has impacted the global weather systems and climate. And she actually got a picture that looked very much like what we saw last February for the next 100 years. So it's possible that a scenario like what we had last year will be increasing in the future. But we don't know. How will the atmosphere-ocean system actually adjust to the climate variability in the form of extreme weather systems? So this adjustment process is one that we discussed before. Weather systems, I gave you an example of a thunderstorm and cyclones transporting heat. This represents an adjustment in the atmosphere to the excess of heat that's built up. But it manifests itself in very different ways in the form of extreme cyclones, typhoons. We don't exactly know where they're going to be or how powerful they will be. But ultimately, the atmosphere-ocean system adjusts to those inequities, if you will, in the solar insolation. Blocking, and this is an interesting phenomenon, and blocking is a term that is associated with what we call a weather regime. And I would give last winter as a great case for a block. A persistent weather pattern that really manifests itself over a period of not just days, but weeks. And that has big implications, for example, the number of snowstorms that exist in the eastern part of North America like last year, but also at the same time, since the atmosphere is like a wavy pattern, in the western part of North America there was an extreme drought. So that persistence of storm tracks is a manifestation of the blocking phenomenon, and we really don't understand how blocking occurs very well. That's a big area of trying to understand how to make better forecasts at longer ranges, like for a week to 2 weeks to 3 weeks. That's transcending the so-called weather-climate interface, which is normally a span of about 7 or 8 days. What are the impacts meteorologically that will be occurring in our area of the world in the context of global climate change? I would suggest that we need to be concerned about at least 2 phenomena, if not a lot more. Number one, ice storms. As the air masses continue to migrate northward, the warmer and moister air masses we're going to have a much better chance of having ice storms. They occur with very cold air, but only situated in the valley. And so the geology is not going to change here over the next several hundred years. We're still going to have the cold air. We had it yesterday. It's kind of like dirt in a bathtub. You have to use Mr. Clean to scour it out to get rid of it. It's very hard to do that. We really didn't change much in our temperatures yesterday, and we persisted with a lot of freezing rain. Additionally, during the warmer season, I think we need to be concerned about the transformations of hurricanes as they migrate poleward. We call this the ET phenomenon, or the extratropical transition, and as tropical cyclones continue to migrate farther to the north, we need to be concerned about the consequences. An excellent example of this was, in fact, Hurricane Katrina, which gave us huge amounts of rain, and not many people really think too much about that. So with that, I will stop, and thank you very much for your attention.